leaving wanting more. Let's start with a new data set. We're going to look at the very beginning. How do we notice an interaction? How do we graph it? How do we talk about it? Which should all be things that you're familiar with. So our data set is a soccer data set. And our goal is to be able to predict how many yards the ball travels based on the temperature and the funding for the arena and the weight of the players. And so the idea is if you give me a player and time of day and funding, I can tell you how far that player is going to travel with the ball during the game. And to keep it simple for this example, we've got no categorical variables, but we do have 3 different numerical variables. So let's just look at the relationship of these variables. It looks like as temperature goes up, the player in general can carry the ball further, which might make sense, right? Warmer temperature, you feel more like getting outside. Funding, boy, that one's a little tough. I don't see much going on there. Player weights. Okay, it looks like most of the player weights are right here in the 250 range. There's a few, there's apparently some really, really large soccer players and some rather small ones. And I would say the bigger the player, the further they can carry the ball. Must be a momentum thing. So let's start by making us a fit. And I'm going to try to predict the yards based on funding and temperature and player weight. Notice I've done plus signs. I'm not going to multiply them. And because that's what this chapter is about, you can probably guess I'm going to need them. And I could just multiply all these together and end up with, I think, eight terms in the model. Is that what it would be? But for your final project, you've got, 16 variables. Let's not do it that way. So let's just pretend we're going to throw these variables in and see what we think. How do you determine whether it's good? Please don't go look at that R squared. Instead, I'm going to look at the residuals. And I'm going to start with the overall residuals for the whole model. And I'm trying to look, do I see patterns here? There does seem to be some curvature, like a little check mark on this side. Here it's not following the QQ plot. Great. Can I fix that? Looking at it a different way shows curvature still. We've got a data point. Oh, look at that. 185. Okay, hang on. Player 185 is the 400-pound soccer player. And if you think that's not good, wait till you see he carries that ball pretty well. So I'm going to say this guy is not an error. I really think he's part of the data set. And he's influential because he's the only super large player. I mean, there's some others that are also kind of large, but he's way out there. So yes, he has importance to the model. He should be. He's the only one that lets us know what happens when you are 400 pounds playing soccer. So there's hints that there's something I can do to make this model better, but I have 3 different variables. So how do I figure out which one needs to be improved? Let's look at the residuals for each of them. When I look at, oh, I forgot to turn off my 2x2 for the part MF row. When I look at funding, I do not see a whole lot of anything. No hints there. How about temperature? Wow! Yeah, now I can definitely see something. How about player weights? Yeah, boy, I'm not really seeing a clear pattern. Now keep in mind, our goal here was not to fix the whole model in one swoop. It's to find the variable that most needs to be fixed. In other words, who is screaming the loudest? And look at temperature. Give me a quadratic. Okay, so let's redo what we just did. I could go back up and just change it and rerun it, but because I want you to have this code, I'm going to actually copy and paste. There I put in temperature squared, but that doesn't mean I fixed everything. Let's take a look. I still see some bending. I still kind of see that check mark. I don't think we're done yet. Looking at funding, still no clues. Looking at temperature, wow, still has a quadratic. And player weights, looks about the same. So how come we didn't fix this? Well, you've got to remember, if you want temperature squared in the model, you've got to have temperature as well. Otherwise, you're restricting the kind of parabolas, and here we could not fit the right parabola. Now we have, okay, better. There's at least been a change. I'm still sort of seeing the swoop. There's a little bit of normality. Now, you'll often see that the tails never quite look right. In the middle, it looks pretty good. This doesn't concern me quite as much as this curvature here. And we still have some data points coming up and saying, yeah, you've got some unusual players, but they're not past the red dashed line. Plus, those players really are unusual, and I really think they should be in the data set. So let's see how each of these is looking. Funding looks okay. We've got a dot down here that's a little unusual. Temperature, much better. Remember how we used to have that squaring thing? There does seem to be a tail down here and a tail up there. but that's pretty subtle. And player weights. Well, most of the player weights are in this range, but do we still see some patterns as these go out? And yeah, maybe kind of these spider-leggy things, but nothing here suggests that what I need is a cubic or a quadratic, right? Because it kind of goes down at the same time as going up. So that's when I start thinking maybe there's a three-dimensional picture, and when it got squished against the player weight axis, what I'm seeing is a squished spider look. But if I had the 3D view, it wouldn't look that way. So who could he be interacting with? Well, my choices are funding or temperature. Funding, though, I don't see much of a pattern. There's that low dot there and low dot there, but they seem to just kind of be somewhere in the middle. Here I see a leg down here and a leg up there. I would guess temperature and player weight seem to have something going on. So I want to take temperature and player weight and make them multiply. But remember the linear term. We had that problem before. If you don't take temperature and multiply it by player weights, then you'll be restricting what kinds of interactions could be happening. So I'm going to put them both in. It might be I don't need them both. And if so, then I will take off whatever ends up being not helpful. But let's give it a shot. That actually looks better. That does look better. And look at my QQ plot. Nice. And even the highly influential points, well, no, that 185 is still very influential because that's the one soccer player that you would never think could make it to the field. Let's look at funding. That looks better. Temperature, beautiful. And player weights. Now, it's still true that most of the player weights are in this range, and so it looks clumped here in the middle. But as far as spread out in the residuals, it seems to be a nice even spread all the way across. I would say the residuals look good. Is it possible some other statistician could look at this and say, I still see a spider leg there and a spider leg there? Sure. And they could keep experimenting. The hope is you're not going to find something terrible that ruins your predictability. You'll only improve your model. The biggest reason I'm not going further is once you have a good model, if you make it more complicated, it's going to be harder to explain. And you run the risk of finding patterns where there is nothing. But it wouldn't be bad if you kept playing with it. So now my goal is to determine whether I need everything in my model. So I go to the summary fit, and I think I need to squish my plots, which is going to cause it to crash unless I clear them. Here's what I've got. Everything in here has beautiful p-values, tiny, 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 except one thing. So the interaction between player weights and temperatures appears to be just temperature and player weights. The quadratic term is only temperature. It's not a quadratic term affecting the effect of the player weights. There's not an interaction or an effect modifier between the quadratic part and the player weights. So if this isn't needed, which, let's be honest, that's the most complicated part of my model, let's redo it, except I don't need this right here. I could put a plus sign. Now, I do have some redundancy because when the computer sees temperature times player weights, it's going to add temperature and it's going to add player weights. And here I said add player weights, which is redundant. So if I want to make this look cooler, I don't actually need to have that there because I'll get player weights out of this term. I shouldn't need to check my residual plot. Oh, and I better size out my window if I do. I'm going to do it anyway, just to show that taking out non-significant terms doesn't affect how your residuals look, and it doesn't affect how those residuals look. It will affect these p-values, which is what we're going to talk about in the next chapter with multicollinearity. There's my new model, all significant p-values, beautiful residuals. I guess the only thing left is to be able to explain this. And if I'm going to explain this, I definitely want a picture first. Even though I realize in the videos I made you go through the wording first, it's because the picture really has the best words. And I wasn't sure if you'd watch me do all the bad words getting to it. Let's start with explaining the effect of funding. Funding is all alone. So if x goes up, y goes up by however much that slope is. That part stays the same. Even though our model is more complex, funding itself is just a simple linear term. You do have to watch the scientific notation. I had to back the decimal off one because of the -1 on the notation gave me the 0.44. But let's go to temperature. This one's going to be harder. How much harder? Well, we have a quadratic, and we also have an interaction. So I am definitely going to want to try to explain this with a plot. So let me make a little bit more room for myself, and that totally messes up the way R draws things. Where's my coefficients? Okay, these are the numbers I need. The rest is just p-values telling me I've got a good model. So let's draw the effect of temperature. And because temperature has an interaction with player, I'm going to pick a low value and start there. How did I know that was a low value? Because while the video was paused, I plotted player weights. So 200, I might do a 250 since there's so many there. 200, 250, 300, and maybe 400. And then for temperature, for my prediction, which is temperature hat or temp fat, that looks like. But that's okay, great. Sequence going from 40 to 90 with a length of just some big number. We'll do 1,000. Now I need my prediction equation, which I can read straight off my output. It's going to be a negative 1.240 e to the negative 2. So I got to move the decimal 1, 2. And then I have the effect of funding. Now, since I'm talking about weight hat and temp hat, if I leave funding out, I'm still going to get a good picture that explains what's going on. But it might be shifted up or down. It might not land in the middle of my data. It might land somewhere outside because the funding is weird. The curvature is still going to be the same. The explanation is going to be the same. But if I really want to have a funding, I need to have a predicted value of funding. Fund hat, and do I even care? No. Except I kind of like something realistic. How about 150? A nice middle value. And I've lost my coefficients. Okay, we did funding. Now we have temperature plus 6.116, and there's no scientific notation. That's nice. Nope, these are predictions. Temp hat. And you just keep going. A couple of things to notice. I put the plus sign at the end of the line so that R knows more is coming. I've made the mistake of putting the plus sign over here, and that will not work. Also, when I do temperature squared, I can just do temperature squared. I don't need that special I notation because that was part of the LM command. But here I have my prediction. So what do? Now I just need to say lines with my yard prediction based off the temperature prediction. And of course I color it red because that's just what I do. Yards hat is not found. Oh, and this is why we pause videos. All right. Now, does that go through my data? No, it doesn't. That's because we've used a player who is super lightweight, and that's unusual. My guess is going to be it's these guys down here that are causing that line to be pulled down. So if we copy and paste exactly what we had before, and now I'm going to have a 250-pound player, which is pretty typical. There were a lot of players like that, except I stayed it red. How about green? Now notice it goes right through the middle of the data because this was the weight that most of the players were. Can you see that on the video? Let's up my line width. Nice bold green. Okay, now I also want to try a 300-pound player, which looks up there. Okay, now I can see what the effect of having a heavier player is. So let's try a 400-pound. This is the heaviest they get, and you can see it's up there. So how would I explain this? As temperature increases, the yards increase, but for lightweight players, they tend to plateau pretty quickly. For heavier players, they don't seem to plateau nearly as well. Our heavy player has not apparently played in super hot conditions, but we really ought to try that because according to the pattern we're seeing here, he might be a masterful player. Of course, this is yard. This doesn't actually say how many goals they make, which is probably because of soccer, you know. 3 goals is a lot. Of course, I don't want to have to write a whole bunch in my report explaining what line means what, so a legend is going to cover up my thing. So let's see if I can do this. I'm going to size this out. Control A, Control R. Oh, that looks nice. It is perfectly acceptable to do a little happy dance when you get a picture like that in your report. But I'm going to delete it after I copy it into Word because otherwise I can't squish it. That was only explaining temperature. We have not yet explained player weight. So I'm going to copy and paste. Let's do player weights. I think it was plural, so they says, yes it is. And what do I need to do? Okay, weight now, because that's what I'm explaining, needs to be a sequence that goes from 200, we'll take it up to 400, the length of something big. And now temperature, because it's the interacting variable, it's not going to be a sequence. It's going to start at something low, which looks like 40 to 90. Please tell me this is Fahrenheit. Otherwise, you just boiled a couple soccer players. So we'll start with 40. Here's the cool thing. This prediction equation doesn't change. We still have the same numbers. It's still the same model from the same data. So that was the hardest part, but now we get to use it over and over. It's not temp hat, it's weight hat, and this is a cold temperature, so how about we color it blue? So we said it worked. Now, why is it a straight line instead of curving? Because temperature had the squaring, not necessarily weights. It does have the interacting effect, which can give it a curvature, but I think this looks about right, especially for a lightweight player. Sorry, no. This does not represent lightweight players. See how you can get this confused? This represents cold temperature. So when the temperature is cold, the ball doesn't travel as much. If we increase our temperature, let's say it's not freezing at 40, but it's at 60. What's blue? We'll make it green because it's a little bit warmer. It jumps up pretty dramatically. Let's do it again at 80, which is pretty hot, especially if we were talking Laramie. We'll make it red for hot. All right, so do I need to go all the way to 90? 90 was the top of the data set. The rule is you need enough to be able to explain it. I think I can see the pattern of what's happening, and so I can explain this all right. I don't think I need to go all the way to 80. I don't need to fill in a bunch in between these two. I feel good with 3 lines, except I can see that I have messed up my color order, which is why we pause videos. Now that is nice. I feel pretty confident about my ability to explain this to a client. So I have my 2 reports. Where would I start? I would have a nice little paragraph about how cool soccer is and how soccer is a big moneymaker, at least in certain areas, which will help you with your fantasy leagues and whatever else, and cheer for your team, Botafogo, which if you don't live in Brazil, you probably don't know who that is. But point is, we want to make it sound like what we're doing here is really interesting. And sports statistics, it shouldn't be that hard. Well, I have a little sentence in there about how we checked for the big data point and we're using R and all the stuff to make it so that the client feels confident that we know our tools. And then I'm going to explain, how did I get to the model I used? Well, first off, there was a quadratic pattern showing temperature needed to be squared. And I'm going to mention that I saw patterns which led me to the interaction. Some students, when they do their report, they like to actually show those residuals so that it helps them explain what they're talking about. And that's great. That's not a bad thing. It might depend on your clients how much information they want. But for this class, you're not going to get punished for not having enough information. And I'm also going to make a note that I took out that temperature squared times player weight interaction. That might be overkill for most clients, but in this class, you need to be able to explain that you thought about that, you recognized it, it just wasn't significant. And the client deserves to have a sentence in there that says, I know how to check that I did it right, and I actually did. So there I have my alpha, they were all significant, randomized residuals. Our model is a good fit for the data. And even if they don't understand that, they'll see that sentence and think, oh, good. Now let's give them the prediction equation, which I can start with what I had in R and just clean it up so it looks nice. Now let's explain thunder, which was the easy one because it was just linear. Now let's explain temperature, which I have this picture ready. Should I explain it before the picture or after? Well, that's a style choice. Actually, some journals do have a preference. So I'm going to mention how it tapers off for the lightweight players. For the heavier players, it doesn't taper off till later. And for the really heavy players, it seems like maybe it doesn't taper off, although we don't exactly have data beyond this point here. So we would need more study, which clients love to hear because more study means another grant proposal. Now that we've explained temperature, can we explain player weight? Yeah, if I size my picture a little smaller. This time I'm going to do an explanation above it, just to show the style. I've purposely decided I'm going to try to write something really terse and short so that you can see the different style. As the temperature increases, the steepness of the line also increases up until the really hot temperature of 80. I'm sure there's some student in Qatar who's watching this video going, 80 is not a hot temperature. Well, you know what? In Laramie, that would be. I think if you went shorter than this, it really wouldn't convey the information. And there's a lot more you could do. I actually paused the video and calculated what are these slopes. If you go back up to the prediction equation and you just look at weight, the slope is 0.3805 plus 0.009256 times the temperature. So doing that, I found out this one has a slope of 0.76, 0.95, and 1.14. So there's a lot more explanation that you could put into this. And I like to try to let you pick the style that works for you. Just make sure that you have explained it well. Now to the part where we answer the client's question. We've gone through the math and shown the picture so they understand the relationship. Let's make some little conclusion that makes it so they actually know what the answer is. And I'm even going to make some conjectures about why this relationship might be happening. And I realize I might be wrong, which is why I said might be. But that shows I've understood what's really gone on and I've thought about the meaning of it. And I'll be the first to admit I really don't understand why the heavier players are carrying the ball more, but it's fun to think about. I don't want to get in front of a 400-pound soccer player. It's got to be muscle, right? Muscle's heavier than fat. And I'm going to include some future study things. Those both look really ridiculous now that I read what I wrote. I just want to know that you're thinking about the idea of studying these things, not just the numbers or getting lost in the data. Let's do another video. I realized this was a long one, but it went through an entire example. Let's do it again.